Hello, everybody. It's Iván Martínez. I'm an master PhD. I'm doing the PhD together with Manuel and Javi in the research group and or in collaboration with my company AM Methods, that is a spin-off of the university. Also with the grant that we get from the Comunidad de Madrid. Kind of the goal of my thesis is to improve the convection prediction for aviation using machine learning. As you might ask, and also it was kind of a question that I had. When I started working in the department, I had heard a lot about convection, that it has been studied for a lot of time, from decades, but it still been a challenge for aviation. And and if you see the news, kind of news in which aircraft suffer from accidents keep grabbing the headlines of the newspaper. Here, all the news that I'm presenting come from 2024. Here it was a flight from Palma to Vienna that encountered a hailstorm, and you see how the aircraft ended at the end of the flight. You can find also many examples. Okay. And you can see a lot of examples like this in the news. To put this visually, here you have a plane that is making a bumpy landing at London Heathrow during a storm. You see how the aircraft swings in a very uncontrolled way that is putting in risk the safety of the passengers. So, I mean, hopefully there was kind of no incident and all the passengers went home nice without any injuries. And on the right part, you see how storms affect the network operation in an airport. Here you see the Atlanta airport, that is one of the busiest airports in the US, and you see that when a storm strikes the aircraft start making holding patterns in order to wait until the storm disappears and they can go through the runway and land. So to put this in figures, what you see here after the COVID pandemic, you see kind of a trend. The important part of this graph is the green bar, in which you see that there is a trend in the weather. In the weather delays, what you see here is the average delay per flight, and you have different causes, and you see that weather is kind of a cause for delay that is keeping increasing. And with the prospects that we have of climate change, the prospect is that the severe weather events will be more frequent and more disruptive. So kind of this figure and this trend, the prospect that we have is that they will keep increasing. Also, if you put kind of the safety factor, let's say aside, that of course is the most important part, but there is also an economical factor, that if you take an estimation, for example, that 1 minute of delay can be kind of estimated to be a loss in the network of 100 euros. If you see the amount of flights that we have per day and the minutes of delay, this problem ends up being also a very huge economical problem. So the idea for this is that there is a need for enhance the weather information that the ATFM and the ATM system is using to improve the decision making. So kind of the index for this presentation, I will kind of briefly explain the state of the art, and then I will go through the scientific goals and objectives. I will discuss a little bit the methodology. It's been 1 year and a half since I started the PhD, so I'm starting working on it, and I still don't have results, and then I will present the achievement that I made so far. As for the state of the art, kind of the reason why you see kind of this convection thing keeps being a challenge for aviation is because stakeholders, typically the information that they have is information that is produced by meteorologists, but by analyzing the numerical weather products. As you see here, some examples from ERMET, TAF, SISMET that come from legacy, but what you see on the fourth one is it's a novel product that started being issued 5 years ago. It's kind of a collaborative framework between the different national weather service providers, in which they collaborate to create risk maps of convection. They generate this product twice a day, but they started doing this in a PDF format. Now there is a server and they integrate it, but the idea is that these products needs to be handmade by methodologies, which limits the frequency update of the forecast. Some of them, like the tabs of the SIDMET, are alphanumeric. Most of them, if not to say all, they lack the spatial and the temporal resolution needed to improve the decision-making process. So this is kind of one of the reasons why convection keeps being a challenge for aviation. What you see here is kind of an idea that was kind of that started here in the university, in the research group of Manuel Soler, that he was looking at these figures before me and kind of proposed kind of this idea of merging, of using the AI to bridge the gap between the numerical weather products and the observations, and see if we can create an AI that can learn from the patterns between these two data sources, and we can eventually create digital product that can be ingested in the decision support tools of the stakeholders. This was kind of an idea that it was successful, and it was granted an European project, ISOBAR, in which a former PhD student of the department, Daniel, did his PhD. Now Aniel is my boss at AM Methods, and all of this research has been channeled into an industrial project, also a European project, in which we are channeling this research into a product that the stakeholders can use, and eventually, if we are successful, they buy. But the idea that we have here is kind of to put the AI in between the numerical weather products that we use, kind of a forecast of the state of the atmosphere, and we try to use the AI to map this state with convection risk that we derive from different data sources. And he'll use satellite aligning to create these maps. The goal of the challenge for the AI is to classify the different states described by the numerical weather products to the different risks. This research resulted into different publications that you see here, and I invite you to read if you are interested. As you see here, we have been tackling two data sources, satellite and lightning. There is another important data source that is commonly used as a proxy for convection, that is radar. And on this part, it's a very active research area in which here the goal of the AI models that have been developed is to kind of create sequence-to-sequence models. So they are fed with a sequence of radar images, and they try to predict the future sequence of radar images. In the end, radar is precipitation. Here you have an example of the NOCAS-net model that at 2023 it was kind of the cutting edge model. Now I have seen that there are others that improve a little bit this model, but it was kind of paving the way of using the radar information in order to generate a proxy for convection. Here you see some of the results in which they used this model to predict the evolution of the front in different storm cases, one in the US and one in China. And what you see is that these new models improve the standard AI models like the prediction recurrent neural network, which tend to give you blurry prediction. With this model, you can get sharp predictions, which mimics what the radar image looks like. Based on the result, we made kind of the experiment of using this model with our own radar images to see to what extent we can leverage on this approach in order to build our solution. Here you see an example. I need to further, let's say, benchmark the results, but as you may see at the first time step, you see that more or less the prediction is good, but then at the end, there is a lot of errors that got accumulated, and also, since this network is using GANs, you get some artifacts. But kind of the scientific gaps and the objectives that I put. Okay, no, but it's okay. The scientific gaps that I see for my thesis is kind of the lack of decision-oriented competitive risk indicator. I think that the most important part when you kind of do industrial research is that your research kind of fulfill the needs of the stakeholders. And in a project in which we are participating, I'm receiving a lot of feedback about the data sources that they trust. A satellite is not one of these data sources, so one of the objectives that I have is to create a more robust risk indication for convection by merging the different data sources that we have available. And also the second part is the insufficient spatial temporal characterization. The numerical weather products that Daniel was using in his thesis were numerical weather forecast with an update cycle of 6 hours, a 1 hour time step that they cannot support at all the convection nowcasting into 15 minutes ranges that is critical for the timely decision making. So kind of the objectives are aligned with these gaps. So the idea is to define competing risk functions that merge radar, lightning, and satellite signals to create risk function that maps the needs of the stakeholders, then incorporate high resolution numerical weather products with an increase in the spatial and the temporal and the temporal resolution, and then the final objective is to create an AI convection nowcasting model that can learn the correlation between the signals from the numerical weather products and the risk function. The methodology I will skip because it's just a kind of an status of the different objectives, but I'm still working on it. As for the competitive risk, I'm let's say grabbing the data and creating the data sets. As for the numerical weather products, in the project in which we are working, we have access to a private forecast, but an important thing is that we need to get access to, I'm also searching for numerical weather products from national weather service providers, since it's key for the stakeholders to use numerical weather products that are coming, let's say, official. So I will use this forecast as kind of as an experiment to kind of prove that this idea works, but when it comes to deploy from industrial point of view, we will need to align with the national weather forecast, with the national weather service providers. As for the achievement, the last slide, before starting the PhD, I was doing my master thesis with Manuel, and the work in which in this work I started working on convection, and finally it ended up in a journal paper that was published last year. And then at the end of last year, I participated in a conference in Geneva of aeronautical methodology. And finally, I completed a course in machine learning for time series and data streams, because the idea of this solution is to deploy an AI that can be constantly improved using real-time data streams. I skip this slide because I don't have time.